Hello, Advanced Geometry. Mitch Donaldson here. I'm just going to continue talking about section 7.1. So far we talked about the algebra that we're going to apply in chapter 7, or some of it. And so now we'll talk about the geometry. So chapter 7 deals with transformations and symmetry. So a transformation is a process in which all points of a geometric figure are moved according to a certain rule. So you're starting off with some geometric figure, like in this case it's a triangle, all right? And then I'm going to do something to that triangle, which kind of moves it, maybe flips it, maybe changes its size, all following a certain rule. Okay, in a transformation, the original figure is called the pre-image because it's before or pre the transformation occurred. And the resulting, I meant to say figure here, the resulting figure after the transformation is called the image. So in this example, this is a transformation of triangle DEF to triangle D prime, E prime, F prime. The image of point A after a transformation of any type is called A prime. That's what that little apostrophe is read as prime. All right. So if you saw this, you should now read it, since you're in geometry, as prime rib. Pretty good one, huh? All right. So I could tell just by looking at this picture that I started with this triangle as my pre-image, the one in the top left there, and then I performed some sort of transformation, and then it moved down here to the bottom right. And I know I started up here and ended down here because you always start with the unprime and you end with the prime. So this shows me that I took this triangle, I followed some rule, and now I have this resulting figure after that transformation. So there are two types of transformations we'll discuss. The first is called a rigid transformation, or also referred to as an isometry. And this is a transformation in which the image is congruent to the pre-image, which means the size and the shape are preserved or don't change. All right? And that's going to be our focus of today's lesson. But there's also what's called a non-rigid transformation, and that's a transformation in which the image is not congruent to the pre-image. It does not preserve size and shape. We'll get to that later. Today's focus is on rigid transformations, or isometries. Isometry. All right, so the first we're going to talk about is a translation. So a translation is the simplest of all of these rigid transformations. All right, you're just going to take every point and essentially, and this is another word for this, by the way, is a slide. Because you're going to take every point and essentially slide them all the same direction and distance. So all points will move on parallel paths the same distance. The distance that point moves is called the distance of translation. And remember, if you want to find the distance between 2 points, we use the distance formula. And the distance formula is the square root of the difference in the x coordinates, x2 minus x1 squared, plus the difference in the y coordinates, so y2 minus y1 squared. And we would use this to find the distance, and we'll do some examples of that later. All right, now let me just show you a quick and easy example of a translation. Look, here is my beautiful dog, Neva, and I want to translate Neva. So the first thing I got to do is tell the computer, remember, a translation is just a slide. So I need to tell the computer what direction to slide Neva and how far to slide Neva. And I'm going to do that by drawing the segment. So I'm going to say, all right, I want Neva to start here, and I want Neva to end here. So I'm going to tell my computer to mark that, what's called a translation vector. You can see it like the little dotted line saying, okay, I'm going to move it from here to here. Now, Neva is not starting at this point, and that's okay. But Neva is going to move in the same direction and that same distance. So when I click on little Neva and hit translate, she moved down and to the right because that's exactly how I drew that translation vector. Now, if I make it shorter, Neva moved less distance away. Make it longer, Neva moved longer away. I could change the direction I want to translate Neva, to down to the left, or up to the left, or up to the right, or down, right? So that is a translation where all I did was just slide little Neva along a path. So we can do that with this triangle here as well. So let's do a quick little example. So I'm going to take every one of these points, I'm going to move them all to the right 4 and down 2. I'm going to slide every point on this triangle, right 4, 1, 2, 3, 4, and down 2. So if this original point was A in my pre-image, the image of that is A prime. And then B is going to go right 1, 2, 3, 4, and down 2. So this would be B prime. And C is going to go right 1, 2, 3, 4, and down 2. So this would be C prime. Now, if I moved all these the same distance and length, then the resulting image, excuse me, let me change this to a segment. The resulting image is going to be a triangle that was congruent to the original. So all I did was translate triangle ABC to triangle A prime, B prime, C prime by following this rule of going right, forward, and down 2. I can describe this move with what's called a translation vector. And I'm going to use vector notation, which instead of parentheses, are these like little squared brackets. All right? And so they kind of look like maybe an angle symbol almost, or a less than or greater than symbol is probably an easier way to describe it. So if I went right 4, remember just like an order pair, the first one's going to be my x move. Put a positive 4 there, meaning, hey, I'm adding 4 to all the x coordinates. All right, and if I went down 2 for the y part, I'm going to put a negative 2. Because just like on a coordinate plane, when you go down, that's associated with negative. This translation vector means move it over to the right 4 and down 2. The next type of isometry or rigid transformation we'll talk about is a reflection. All right, this one will make a lot of sense. You guys know what a reflection is. It's going to produce a mirror image. So first thing I got to do is I got to tell the computer where I want that mirror to be. So I'm just going to draw some line, and when I double click it, I'm saying, hey, make that my line of reflection or my mirror. So now I'm going to reflect little Neva across that. There she is. You can see I got a mirror image. Notice on this pre-image, her little leg is sticking out there on the left, and in the image, the reflection, it's sticking out on the right. I know she kind of looks a little symmetrical in that picture already, but you can kind of see that it's a mirror image of that original picture. And the closer I have Neva to the original line of reflection, then of course the closer her reflection is to that line. And the same if I move it further away. And you don't have to reflect over a vertical line. You know, I could tilt this line and the reflection brings Neva down there, and so forth and so on. There you go. There is a reflection. So let's do that with this triangle in this diagram. All right, so I'm going to start off. I need a line of reflection, so maybe I'll just put one that's just like 1 unit to the right of C there. And I'm just going to reflect over that line. So if C is 1 to the left of that vertical line, C prime will be 1 to the right. If B is 1, 2, 3, 4 to the left, then B prime is going to be 1, 2, 3, 4 to the right. And then if A is 3 to the left of that line, then A prime is going to be 3 to the right. And now I simply connect the dots, and I got my reflection. There you have it. You can see it's a mirror image of that original diagram. All right, and then the last one is a rotation. So in a rotation, all points rotate the same number of degrees around some sort of center point, okay, that you're going to plot. There's 3 things we need to know. We need to know the center of rotation, the degree of rotation, and the direction of rotation. When I say direction, I mean clockwise or counterclockwise. If no direction is given, it is assumed that the rotation will be counterclockwise. Why is counterclockwise the default? I really don't know. It just is. So let's rotate little Neva. I need 3 things. First, I need a point of rotation. I'm going to rotate Neva around that point. All right, so I'm going to click on Neva. I'm going to rotate her. Notice how the default was a counterclockwise rotation. I say I want to rotate Neva 100 degrees, and it rotated her counterclockwise because that's the default rotation. All right, maybe instead of 100 degrees, I only wanted to rotate her 60 degrees. All right, maybe instead of 60 degrees, I want to rotate little Neva 180 degrees. Okay, that should be halfway around the circle, and look, there she is down there. All right, now, in my computer program, if I want to go clockwise, which is not the default direction, I'd put a negative in front. So maybe I want to rotate clockwise 90 degrees. There you have it. And that, my friends, is a rotation. You'll notice the image of little pre-Neva gets moved around as I move my little center of rotation. But essentially, in this case, Neva was rotated 90 degrees clockwise. All right, and that's exactly what we're going to do with this one here. We're going to rotate this triangle 90 degrees clockwise. All right, so to do that, I'm going to put a little center of rotation. Maybe my center of rotation is right here. And let's rotate the points. Now, if I want to go 90 degrees clockwise, and the reason I chose 90 degrees, you guys, is because I understand that 90 degrees makes perpendicular lines, and on a coordinate plane, I can do perpendicular by using opposite reciprocal slopes. So, for instance, if from C to my center of rotation is a horizontal line of 2, then C is going to be, or C prime will be on the vertical line that's 2 away. So here's C prime. I rotated it 90 degrees clockwise. Now B. From B to the center of rotation, I go down 1 and over 1, 2, 3, 4, 5. Down 1 and over 5. Well, if I want perpendicular to that from my center of rotation, I'm going to go up 5 and over 1. So up 1, 2, 3, 4, 5 and over 1. This would be B prime. And then A, to go from A to the center of rotation, I go down 1, 2, 3 and over 1, 2, 3, 4. So now, in order to get the perpendicular to that, the opposite reciprocal is 4/3. So from the center of rotation, I'm going to go up 4, 1, 2, 3, 4, and over 1, 2, 3. There's A prime. Now, you guys, that's a bit confusing, and don't worry, we're going to talk more in detail about how you do rotations later. Today is just an introduction. There you have it. There's my 90-degree rotation, 90-degree rotation of triangle ABC to triangle A prime, B prime, C prime. All right, and the next thing is what's called a reflection line theorem. It says the line of reflection is the perpendicular bisector of every segment that connects a point from the pre-image to its corresponding point in the image. So check this out. If I want to find the line of reflection to apply this, perpendicular bisector. Bisector means go through the midpoint. So all I really have to do is just connect the image and its pre-image, image and pre-image. And I'm going to create perpendicular bisectors of all those segments. Well, bisector means it goes through the middle. So I'm just kind of looking at my diagram, looking at these red segments, and kind of guessing where that midpoint is. And now, if it's going to be perpendicular to that, I'm going to use slopes. Notice the slope of each of these lines is down 1 over 2. Down 1 over 2. Down 1 over 2. Well, the opposite reciprocal of that would be 2 over 1. So to draw my perpendicular line, I'm going to have a slope of up 2 over 1. Notice that's exactly where the next midpoint is. Up 2 over 1, that's where the next midpoint is. So all I got to do is follow that rule, and now I can draw my line of reflection. And there it is. And this problem wants me to give the equation of that. Well, to give an equation, I need a slope and a y-intercept. Well, the slope of this line is up 2 over 1, my line of reflection, the red line that I drew. And the y-intercept is at right here, 0, 1. So to write my equation in slope-intercept form, y equals mx plus b, it's just y is equal to 2x plus 1. And the last little thing today is just symmetry, and we'll just kind of do this quickly. How many symmetries does a figure have? A figure can have multiple lines of symmetry and many different rotational symmetries. Also, a figure has, or every figure, has 360-degree rotational symmetry, but we don't call that figure symmetric because that's the only type of symmetry it has, and everything has that. So here, let's just do an example and see what we're talking about. Draw a large capital letter A. Here it is. Did the best I could to make it nice and pretty. How many lines of symmetry does it have? Well, you guys should see that there's one line of symmetry. I kind of missed, but you get the point. Let me try that one more time. One line of symmetry. So there's one line of symmetry I could draw. Does this figure have rotational symmetry? What I'm asking is, can I rotate that A 90 degrees, 180 degrees, 500 degrees so it lands on itself, right? This figure will only land on itself if you rotate it all the way around 360 degrees. So because of that, it does not have rotational symmetry. That's not very special because every figure could rotate 360 degrees and land on itself. But let's look at the letter H. Now the letter H, on the other hand, has two lines of symmetry. Look, there's this vertical line where you could fold it over and it would land on itself. Boom, boom. And there's also a horizontal line where you could fold it over, and I kind of missed, where you could fold it over and it would land on itself. So H has two lines of symmetry. Now what about rotational symmetry? Well, if you think about that letter H, if I were to rotate it, oops, let's see, I'm going to run out of time, but I wonder if I can do this. It's not letting me grab it. But you're just going to have to visualize this. If I flip this H and rotate it 180 degrees, it would land upside down. So it would have rotational symmetry of 180 degrees. Hey, we're out of time. We'll finish this discussion later.